Adjoints. Adjoints are a little bit confusing, so we're looking at them in a couple of different ways. And I'm going to do one particular careful way today. So one of the tools we need is this theorem called the Riesz representation theorem. Riesz representation says for all phi, concisely, for all phi in V star, V is an inner product space, there exists a unique vector V inside of V such that the linear functional phi can be represented as the function inner product with V. So that's a very concise statement of Riesz representation. And we gave the proof already. And now we want to think about adjoints. We saw one way of defining them. Here's another. Suppose I'm going to define now an element of V star. An element of V star so that I can apply this theorem. So I'm going to define a phi, which goes from V to the field F. And I'm going to define it in two parts. First, it's going to have an intermediate space, which is W. Okay, so I'm going to give you an element of phi by giving you a map from V to W, which we'll call F, and a map from W to F, which will be an inner product with something. So the function is going to say, it's going to take V and send it to F of V, which is of course contained in W. And it's going to take F of V and send it down to the field. So I need to define an element of W star. And the element that I want to use is inner product with W. So I pick an element W, a vector W in W, and then I form the function inner product with W. That's a perfectly good linear function. So I have a composition of two linear functions. So phi is the composition. First I apply F, and then I apply the function inner product with W. Another way of saying that, so phi is composition of inner product with W. First F, then inner product with W. Another way of saying that is that phi of V is the inner product of F of V and W. And that defines a perfectly good element of V star. Now I can apply, right, so this thing, so phi is in V star. So now I can apply this theorem. It says that any time I give you a phi in V star, there's a unique vector in V. I'll have to pick a different name because I already used little v here, such that that element phi can be represented as inner product with that. So by Riesz, there exists a unique vector, let's call it Z, in V, such that phi is inner product with Z. And we're going to give a name to that vector. We're going to call that vector F star of V. F star of W. That is, this theorem tells me that there's a unique such vector. Because there's a unique such vector giving that data, I can view this as a function that fixing F, takes an element of W and defines an element of V. Now at this point it's just a function. It's not necessarily linear. But we have, by definition, the inner product of F of V and W, and that inner product takes place in W, is equal, by definition of this, to the inner product of V and f star of w. That's just the definition of f star. It's the thing that solves that equation. This is called an adjoint equation. It has a solution by this theorem. It has a unique solution. So this thing f star is a function from w to v. And all we need to do is to show that it's linear. So at this point, it's just a function. So we defined it last time in a different way. Defined in a different way, it was automatically linear because we composed linear functions. Here, we're defining it as a solution to an equation. We know that thing exists, but we haven't shown that it's linear. Okay? So to show it's linear, we need to show that it respects addition and scalar multiplication. That is, if I have w, it's a map from w to v. So if I have two elements of w and I add them together, I want to show that I get the same answer. So by properties of the inner product, I can write this as f of v w1 plus f of v w2. That equals, by linearity, or by definition of this adjoint, this is by definition of f star. The definition we gave here, that's equal to, I can rewrite that as this, and I can rewrite that as the inner product of v and f star of w2. And then by additivity in the second slot of the inner product, this is equal to v inner product with f star w1 plus f star w2. And so this is kind of one of those guess and check proofs of linearity. That is, what we see here, this equals that, is a version of this adjoint equation with the input w1 plus w2, right? It says this vector here, whatever it is, solves the adjoint equation. Because we know the solution is unique, it must be equal to whatever f star. So f star of w1 plus w2 is by definition whatever I need to plug in here for this to be true. This works, and therefore they must be equal. So that's the linearity part. I can make the same kind of argument for it respecting scalar multiplication. So if I take fv and a times w, and I want to figure out what's on the other side, I can pull out a at a cost of conjugating it, because it's conjugate linear. I can move f to the other side at the cost of changing to this f star, the cost of this adjoint. And then I can move the a back in over here by conjugating again. So I get v a f star w. So again, this tells me that the vector a f star w solves the adjoint equation, whose left-hand side is this, and therefore it must be that the solution to the adjoint equation for the input aw is equal to this solution, this particular solution, because there's only one. And so it's homogeneous. And therefore it is linear. Let's talk about some properties of the adjoint. I won't give the proofs of these, but you should check them. Something I might ask you to look at in a quiz. And these are properties quantified over FG linear maps from V to W and A field element. The adjoint of a sum of linear operators is equal to the sum of the adjoints. If I have a scalar multiple and I take the adjoint, I have to conjugate the multiple in order to pull it out. The adjoint of the adjoint is the input. There are some functions, some linear maps. If they're operators, if they go from a space back to the same space, it's possible for them to be equal to their own adjoint, right? If the domain and the codomain are different, that's not possible. But if they're the same, like for example, the identity transformation, if its adjoint will go from V to V, and in fact, in this case, the adjoint of the identity is itself the identity. And finally, if I multiply two, rather compose two linear transformations, so say they're operators or there's three vector spaces involved, that's equal to the composition in the opposite order of their adjoint. So a warning. Here are three symbols that you might see. This one pretty much always means adjoint. This one sometimes means adjoint. In this book, in this class, it means adjoint. This one always means transpose. This one sometimes means transpose. So sometimes these two are equal, sometimes these two are equal. These are always not. Okay. So in this class, this one doesn't really exist. We just have these two. So this is adjoint, this is transpose. I just want to warn you about that piece of inconsistency in the notation. So let's look at some properties of this adjoint. And we know that it exists, and it's a linear transformation that goes in the opposite direction. First of all, it interacts in a very nice rigid way with ranges, null spaces, and orthogonal complements. Suppose I have a linear transformation from V to W. Then the null of F star, the null of F adjoint, is equal to the range. The null space of the adjoint of F is equal to the range of F, its orthogonal complement. The range of the adjoint of F is equal to the null of F's orthogonal complement. The null of F is equal to the range of F adjoints, orthogonal complement, and finally, the range of F is equal to the null of F adjoint, its orthogonal complement. So for the proof of this, we're really just going to prove one of these statements, and then the rest of the statements follow by a very similar argument. So let's look at the first one, A, and consider what it means to be in this null space. Suppose W is in the null space of F star. This is true if and only if, I'm going to give a bunch of equivalent conditions until we get to this one. This is true if and only if, well, by definition, f adjoint of W is equal to the 0 vector in V. That's true if and only if the inner product of V and the f adjoint of W is equal to 0 in the field for all V. In V, since the only vector that's orthogonal to everything in V is the 0 vector. I'm just using that trick. So that holds if and only if f of V, using the adjoint now, inner product with W equals 0 for all V. Why are these two the same? Because by definition of adjoint, that adjoint is the thing that makes these two inner products the same. And that's true if and only if, well, this is an arbitrary, f of V is an arbitrary element of the range of f, and W is something that's orthogonal to it. So that's true if and only if W is orthogonal in the orthogonal complement of the range of f. That's what's over here. Okay, so W is in the null of f star if and only if W is in the range of f orthogonal complement. And then if we take this equation, null f star is range of f orthogonal complement, and we complement it, we know the double complement is equal to nothing, and then we get another statement, this statement. D, that's D. And then for B and C, you just make the same argument as this one, interchanging where the f and f star go. So it's all really just this proof, this chain of equivalences. So in a second, we're going to talk about the matrix of a linear transformation. And if you write the matrix of a linear transformation in an orthonormal basis, then the adjoint amounts to the conjugate transpose, which you may have seen in a more matrix-oriented class. To highlight what's going on there and the specialness or the tight relationship between the orthonormal basis and the inner product, I want to make the following proposition. So let V be an inner product space and E1 up to En an orthonormal basis for V. Of course, I know that I can take any vector in V and write it as a linear combination of the elements in the basis, in the orthonormal basis. And I have, moreover, an easy way of computing the coefficients by taking the inner products. And so I should be able to express the inner product in some easy way. And that's true. And here it is. I equals 1 to n. Inner product of U and EI. Inner product of V and EI conjugate. So what this says is that when you're computing the inner product of two vectors with respect to an orthonormal basis, it's the same as the dot product. Another way of saying that is that embedded in the notion of an orthonormal basis for a space is a particular distinguished inner product. So if I write just a vector in sort of Rm with a standard basis, that distinguished inner product is the one given by the identity matrix or by the dot product. I can conceive of other inner products by writing down other positive semi-definite matrices, but if I do that, positive definite matrices, if I do that, the basis that I started with will no longer be orthonormal. Okay, so they're intimately connected, so let's prove that. Well, okay, U is a sum from I equals 1 to n of U, EI, EI. That's our trick for writing any vector in terms of And the same for V. V is the sum from j equals 1 to n, inner product of V with Ej, Ej. And then the inner product of U and V, I can just expand them using this expression. Now I get a giant inner product with two big sums in it. I equals 1 to n U Ei, Ei. Inner product with j equals 1 to n V Ej, Ej. That's, I haven't changed anything. I just expanded U and V. And now if there were, if n was equal to 2 there, and I broke this out using the additivity in both slots, I would get a 4-term expression. And for an arbitrary n, I get an n squared term expression by expanding it. That's the sum from I equals 1 up to n, the sum from j equals 1 up to n of, well, it's a big inner product. I mean, a little inner product, just because all these coefficients have little inner products in them. U, Ei, Ei, V, Ej, Ej, and then I close the big inner product. So this is just a scalar. This is just a field element. That's just a field element. I can pull those out, but I have to remember to conjugate the second one. So that's equal to the sum I equals 1 up to n, sum j equals 1 up to n, U, Ei, V, Ej, conjugate, because I pulled it out. And then what's left over is just the inner product of Ei and Ej, Ei, Ej. But we said the e's are in orthonormal basis, so this product here is just either 0 or 1. It's 0 if I and j are different, it's 1 if they're the same, so I can simplify this and get rid of one of these sums. I equals 1 to n, U, Ei, V, Ej, conjugate. That's what we wanted to prove. Okay, so once we fix an orthonormal basis, we fixed an inner product, the dot product. If we wanted to change our inner product, our orthonormal basis is also going to have to change, or it will stop being orthonormal in general. So the reason for reviewing that is so that this next theorem doesn't cause any confusion. So suppose I have a linear transformation from V to W, and I have two bases. E1 up to En is an orthonormal basis. For V, and C, G1 up to Gm is an orthonormal basis for W. Then the matrix for, okay, so there's two matrices here. F star, F adjoint, is going to go from W to V, and that means it will be the matrix with respect to the basis C first, then B. The matrix of F star, I want to explain what it is in relationship to the other matrix. And what it is it's the conjugate transpose of the matrix going in the V to W direction of F. And it's very important, of course, that these be orthonormal bases. So the proof is just thinking about what each of these matrices are, writing it out. So F sends each basis element to a linear combination of the Gj, and this is the kth column of the matrix with respect to B and C of F. And by orthonormality, I can compute the coefficients, namely F of Ek is F of Ek inner product with G1, G1, and so on, F of Ek inner product with Gm times Gm. So these are the coefficients that show up in the matrix. If I make the same computation for F star, expanding the image of a basis element of a G basis element, I get this. F star of Gk is the inner product of F star Gk with E1 times E1 plus the inner product of F star Gk En times En. So the entry in row J, column K, of the MCB of F star is the inner product of F star Gk applied to Gk and Ej, which by definition of adjoint, or by the adjoint equation, is equal to the Gk inner product with F of Ej. I can exchange the order here at the cost of taking the conjugate. So that's that order exchanged conjugate. And so the relationship between this coefficient and that coefficient is that I switch J and K and I conjugate. So that says that the matrices are the conjugate transpose of each other. Okay, so now we're actually getting into the next chapter, and we're going to specialize from considering linear operators connecting two spaces, linear transformations, to linear operators on a single inner product space. And the reason to do that is that we can now talk about things like identity, which are their own adjoints. So F in LV, the in inner product space, is called self-adjoint, or permission, if it's equal to its own adjoint, F equals F star. So if we have an orthonormal basis for V, that's an orthonormal basis for both the domain and the codomain, and that says that the matrix of the operator is equal to its conjugate transpose. If I have an orthonormal basis, it also says if I have a real matrix is self-adjoint if it's symmetric, right? Because the conjugate part of the conjugate transpose goes away if we were thinking of the basis as the orthonormal basis. So self-adjoint operators are actually extremely common and are used to represent lots of systems. Examples include things like covariance matrices, adjacency matrices of a graph, or operators, physical observables, like quantum observables, Hamiltonians, and things like that. One other comment is that you should think about, so suppose I have V is one-dimensional. That means that linear transformations amount to scalar multiplication, right? F of V equals alpha V. The matrix of that linear transformation is the one-by-one matrix containing the field element alpha. It's equal to its conjugate transpose if and only if alpha equals alpha bar. Alpha conjugate, that is, if it's real. So one-dimensional self-adjoint things are just reals as distinguished from complex numbers. And so you can think about self-adjoint operators as being kind of the operator generalization of a real number, sort of like a higher dimensional real number. And there are other ways in which that analogy is apt that we'll see as we continue. So to continue with some properties of these things, reasons why we like them, every eigenvalue of a self-adjoint operator is real. So why is that? We'll take F self-adjoint. Lambda an eigenvalue. And V some non-zero vector that satisfies this eigenvalue equation. And consider what happens when I take lambda times the square of V, or in other words, I put lambda V on one side of an inner product and V on the other. Because it's an eigenvalue, because of this, that's equal to F of V, V. And I'm setting it up so I can use self-adjointness. So by self-adjointness, I can move F to the other side, V, F of V. By the fact that it's an eigenvalue, it's V lambda V. And then using the conjugate linearity, so the fact that I can pull lambda out at the cost of conjugating it, I get lambda bar VV equals lambda bar squared norm of V. And so since V was non-zero, its norm is non-zero. Its squared norm is non-zero, and it must be that lambda and lambda bar are equal. And the only way that can happen is if they're in fact real. Couple other propositions. Suppose V is a complex inner product space. F is an operator on V, and the inner product that showed up over here, F of VV, is equal to 0 for all V and V. Then we can conclude that F is just the 0 operator. So I'm going to omit the proof. You can look at sort of a computation. You can look at it in the book. But let's think for a second about the counter example. So I required this hypothesis complex if I just allow it to be a real inner product space. It's not true anymore. So you want to think about the distinction between real and complex vector spaces. You can almost always see the difference by thinking about this two-dimensional space and what happens in these pathological two-dimensional spaces where I have something like rotation. It doesn't have an eigenvector, right? And in this example, that's exactly what's going on. That is, the counter example is if I act by the linear operator, which is rotation, by 90 degrees, that causes the input and the output vectors always to be orthogonal. But it's certainly not the zero operator. In fact, it's a bijection. Okay. And so that's what's special about the complex, is that you have something else going on. And do a corollary for that. So let V be a complex inner product space. And F in LV. F is self-adjoint if and only if the inner product of F V and V is real for all V and V. And for the proof, FVV, excuse me, we measure whether something is real. One way to measure something is real is by subtracting the conjugate from the item and seeing whether or not that's zero. So if that's real, if that's zero, then we're in the situation of being real. So we'd like that to be zero, and we can compute what that is and see what happens. So by conjugate linearity, I can rewrite that as f of VV minus V f of V. That is, I can get rid of the conjugate by the cost of flipping the order of the inner product. That's equal, by definition of the adjoint, to f of V, V minus f star V, V, which by linearity of the inner product is equal to f minus f star applied to V, inner product with V. And so you can see that if this is zero, so if it's real, then for this to hold for every vector V, so for this thing to be orthogonal, we would need this to be zero. And conversely, if f and f star are already equal, this thing is zero, and this will always be zero, and so this inner product will always be real. The last proposition I want to mention today is that F is self-adjoint, and this F of VV, quantity 0 for all V and V, implies that F is 0. So we already handled this situation in C, so this is really a theorem about real inner product spaces. And the proof, you have to kind of think of an idea, and the idea is this: f of u w is the inner product of a more complicated way of writing it. It's kind of like a parallelogram type of thing. F of u plus w minus f of, this is inner product, minus the inner product of f u minus w, u minus w. That whole thing is divided by 4. Just so happens that works out. You can check it. So f of vv equals 0 implies that this right-hand side is 0. And so inner product of f of u and w is 0 for all uw, and f is 0.